Hello, we're Team 6 and our senior design device is SepSpec, which is a low-volume lactate detector, a solution to a very serious problem. In the United States, 1 in 3 people who die in a hospital die from sepsis. Sepsis treatment is an estimated $24 billion in annual costs, making it the most expensive condition to treat in the entire U.S. healthcare system. Current studies show that the time it takes for doctors to start with antibiotic treatment to treat sepsis is on average 3.43 hours. In the US, the most commonly used diagnostic test is a regular blood test, the results of which take about 60 to 90 minutes to come, and the test uses up to 1 to 3 milliliters of blood, and this poses certain health risks such as anemia in younger children. Lactate levels rise in patients who are at an increased risk of getting sepsis, and that is why having an indicative test would not only reduce the number of deaths to sepsis, but it would also decrease diagnosis time.
Yeah, so now on the current solutions available for diagnosing sepsis, the first and foremost is the blood test, which takes approximately an hour, and it's available at hospitals and laboratories. Secretion tests take a bit longer than an hour to deliver results, but these are also available commercially as well as in hospitals or laboratories. And finally, the Imagine test delivers results on a time frame a bit longer than an hour, and these are sold commercially as sold by a company, and so all of these only have a singular method of detection, either colorimetric or spectrophotometric, but our device, the SepSpec, actually has both, which makes it unique and allows us to maintain the accuracy of a colorimetric test while keeping the precision of a spectrophotometric test.
We spoke with Dr. Srinivasan, Dr. Kelly Benish, Dr. Kathleen Looms, and Dr. Liz Rand, who are all attending physicians associated with the critical care department at CHOP, to list down some general user needs. We decided that there should be a device that is able to calculate lactate levels in blood with clinical relevance, that can deliver results faster than a regular blood test does, which would be ideally under 60 minutes, that is easy to use and compact enough to use in labs, and that can also be used in low resource settings other than just labs and hospitals, and that is also affordable. So the approach we took at creating a device was a step-by-step process. This process included performing the reaction that produces lactate, designing the paper microfluidic device, focusing on spectroscopy to test for sepsis, and then the integration of all the components into the device itself, and then finally testing the device using blood serum.
This is our reaction, which uses the enzyme lactate oxidase to react with the high levels of lactate in a septic patient's blood and produces an iron 3 complex that is orange and absorbs light at a wavelength of 560 nanometers. This reaction is mainly limited by the enzyme in speed, and which is able to process about 1 millimolar of lactate per minute. Our paper microfluidic device helps us with several of our goals. They can be produced very inexpensively and help keep costs down for us and for the users. They can be purchased separately, so you only have to buy the device once and just buy refills, which also saves money and resources, as well as keeping the investment in that one device very effective. Lastly, the reagents can be pre-made to make the entire process very easy for the user and to prevent error. We designed our reaction to produce a chemical that we would be able to detect via spectroscopy, because it is a cost and resource effective way to detect change in concentration and can still help in determining valuable data about our samples. We made a spectrophotometer that is able to read absorbance at 560 nanometers, which is specific enough to get our data and not pick up too much noise. We then integrated all of the previous parts into our device, as well as designed a casing to hold our circuit, the microfluidic device, and the LCD, while still keeping the total volume of the device small for easy handling and mobility.
So now moving on to testing with blood serum. Here we have a calibration curve before serum with an R-squared value of 0.99, and here we have it for a range of 0 to 5 millimolar. And so we tested our device using bovine blood serum, which was artificially brought up to high levels of lactate concentration. And so when we tested with blood serum, noise was brought into the model as expected, but our device still provided clinically relevant information. If you look down to the second graph, our R-square value is slightly lower, but still very high, indicating that the model is still a good linear fit for this data over this range. And I'll talk a bit more about that, the specifications.
Before designing our device, we had a number of goals in mind. We aimed to create a device that could detect lactate using a minimal volume of blood, that has a sleek, modern, and compact design, that could produce results faster than current solutions do. Blood test results take about 60 minutes to come, so we aim to create a device that could produce results faster than that. A device that is both affordable and accurate, and a device with an LCD display screen for it to display lactate levels.
So now the lactate detection range of 1 to 5 millimolar, that is clinically relevant as concentrations of lactate above 5 are associated with septic shock and can become fatal. So another thing is the maximum sample volume. The low volume used of 150 microliters was chosen to avoid health risks involved with anemia, specifically in children and neonatal cases. And finally, the throughput of 20 minutes per sample is calculated based on the total reaction volume and the amount of lactate oxidase in reaction.
Now, to our SepSpec device design. The mechanical device was designed using SolidWorks, and it consists of 3 parts: the top, the body, and the base, which are all screwed together to form a dome-shaped hemisphere, as you can see to the right. At the top left is the image of the top of the device, and you can see that there is a slit for the entry of the microfluidic test strip. The rectangular cutout shown above the slit is for the LCD screen, and the red button is to turn on the device, while the yellow button is to recalibrate the device. The video on the next slide shows an exploded view of the device assembly. The diameter of this device is under 3 inches, and this ensures that the device is as compact as possible. The device was 3D printed using the Prusa 3D printer. Black PLA material was used for a black matte finish to give it a sleek, modern touch.
Shown here is a simplified version of our circuit design that helps highlight the key components. The TSL works to convert the absorbance of light into frequencies that can then be used by the Arduino to relate to concentrations of lactate. The 2 push buttons help with the user interface and help keep the use of the device very simple and quick. This is a quick rundown of the procedure to use our device. We intentionally made this simple so that the process could go as fast as possible, since the purpose is really to get critical information to healthcare providers quickly. First, calibrate the SepSpec with the pre-made calibration strips by pressing the calibration button and inserting the pre-made strips one at a time and pressing the read button for each one. For the actual sample, place fresh blood serum onto the testing strip and wait for 5 minutes for the reaction to complete. At the 5-minute mark, insert the strip into the device and hit the read button, at which point the results will be displayed on the LCD screen. For our results, this is the average calibration curve for our device when using blood serum, and tried at several different points. As shown here, we can get a pretty good regression curve when using our device, and the Arduino calculates this every time it is recalibrated to keep the device as accurate as possible. Some of the other tests we would have liked to run include calibration durability, variability of the device, and expiration of the microfluidic.
So now moving on to major results. Here we have reaction time for our 3 batches for 5 millimolar test strips. And you can see for the time to react, it's they're all approximately 5 minutes, plus or minus a standard deviation of 30 seconds. And they all fit within that, so we were able to create consistent test strips. And so when you compare that to the average time comparison for the CHOP lab time, we actually deliver results 6 times faster than the status quo. So now on to cost analysis. I'm only going to highlight the major components. We have our TSL 237 light to frequency encoder, which allows us to convert our light data into frequency data, read in through our Arduino, analyzed and processed, and converted using our calibration curve into concentrations displayed on the LCD display. Our estimated price for the device would be $150, and I'll talk a bit more about that on the next slide. So now on the price comparison, we compare this against the gold standard, which would be the hospital blood test. Our device is $150, and per test only costs $0.25. And so comparing that to a hospital blood test, this could actually range anywhere from $100 and $1,500, depending on the insurance and the location of the hospital. However, our test strips, we would be able to sell a pack of 40 for only $10. So as you can see, when compared against standards, we actually fall below the price range. And so this is especially better than online blood tests, which are definitely cheaper for $45 per test. However, the delay in response for these, you need to send in your sample and then wait weeks to get it sent back. And so this is clearly not as good as our device. And so moving on to the future, some things we'd like to fix are the light interference of our device, working on our filtration and refining the reaction, enhancing the result time to deliver faster results, meeting with more medical and ICU personnel so that we can better evaluate their need and meet it with the device, and finally, improving fabrication by using industrial-grade equipment.
Finally, we want to address the impact of this device. We aim to solve key problems in the diagnosis of sepsis that will improve treatment and patient outcomes. We aim to do this by quickening the response rate for patients in moderate to severe conditions, using this device in places where other methods are not viable or accessible, and hopefully this can lead to saving lives that were previously caused by inefficiencies in diagnosis, and as well improve the medical expenditure on treatment.